From the brilliant minds that almost brought you the concept of the cat bit, Benjamin Kelly, Rach Costa, and Dakota Harkins bring you a revolutionary fire alarm system. In Australia, bushfires and house fires are particularly dangerous in the hot and dry climate. They can be attributed to over 100 fatalities every year within Australia alone. Often in a house fire setting, smoke detectors provide life-saving minutes before escape is impossible. However, for external fires, such as bushfires or fires in nearby homes, these systems are rendered useless. Often it's up to residents to be listening to news or radio, or even firemen knocking on doors before citizens realise that they are in danger. What's even worse is that due to the nature of Australia's bushland and climate, fires can move very quickly and change direction unexpectedly. The Rural Fire Service of New South Wales keeps a live monitoring of all current fires, whether they be house fires or bushfires, and a rating as to whether they are under control or not. However, this has never been linked to an alert system for residents, and therefore residents must go to the page manually if they wish to see any fires that are near them. Our team researched these issues and discovered that there was a major gap in the ability of our citizens to be actively informed about their safety in regards to fires nearby. Should this gap be filled, it could also be extremely beneficial to firefighters, as citizens would be better informed and potentially require less herding in the case of an evacuation. Together, our team came up with our key problem statement. How might we provide earlier warning for the evacuation of a dwelling in the case of fires outside of the dwelling? Our team knew that we needed to meet certain specifications. Like any normal smoke alarm, the system's sensors must identify and alert the presence of an uncontrolled fire in under a minute. The system must alert users through sound feedback in the case of an immediate danger. The system will also utilise external data, like from the Rural Fire Service and other smoke alarms nearby, to monitor and generate alerts. The system must alert users through minor audio feedback in the case of a nearby fire that is under control. The solution would also allow users to view major changes in their environment, like air quality and temperature, and view these changes graphically over a period of time on the portal. All data that the system collects must be processed, stored, displayed, and analysed, and if required, alerts should be sent directly to the user's phone or dashboard. The system is required to send status messages to the user regarding the node's battery status in the event of major metric changes. The system must store data so that we can report incidences and produce periodic logs for the dashboard. After considering the context and these specifications, our team began developing FireConnect. The concept is simple. Imagine if your normal smoke alarm could talk to other smoke alarms nearby and the fire service to let you know if there was any fire close by outside your home as well as inside your house. Now imagine if it would be able to communicate with you even if you weren't at home. The great thing about the system is that the dashboard would also allow you to keep track of other metrics in your home, like overall temperature and air quality. So how does it work? The system utilises the power of machine learning to visually recognise a fire, as well as to continually check for smoke and the temperature of the room. A network of fire-connected devices all send data back to our system so that we can monitor if there are other alerts close to you. And this data is combined with data received from the Rural Fire Service APIs. All this data is then analysed and displayed on your portal, where you can view fires within different radiuses to your house and your overall metrics. If an alert needs to be raised, this will be sent to your designated mobile number, as well as appearing on your dashboard, and if required, the smoke alarm itself will give audio feedback to indicate immediate danger. So where can you buy one? Well, hopefully one day this system will be available in Bunnings all across Australia. But for the moment, we are still in the prototype phase. Some of our key functionality has been built to offer a proof of concept, and we are happy to be able to demonstrate this for you today. But first, I introduce Rach Costa, who is going to explain her amazing machine learning component of the system.
Hello, my name is Rachel Costa, and I'm going to take you through the machine learning aspect of FireConnect, the fire detection and warning system. This integral part of the prototype was developed from the idea that fires cannot be detected in a timely manner without the introduction of sight, in addition to providing temperature and smoke metrics. I say sight, as taking images without analysis is a fruitless task that would not provide any benefit to the system. But by introducing a convolutional neural network trained for fire detection, we provide our system with an artificial sensor sight that can detect the presence of these anomalies accurately and faster than the system's other sensors in isolation. Considering this is my first neural network, I had to do a lot of research in regards to which kind of network would be the most appropriate and the process of making it. I settled on creating a convolutional neural network, as their primary purpose is to categorize images based on a list of predetermined categories. For our CNN, the predetermined categories were fire and normal. I then needed to create a dataset for our neural network to train upon. I decided to use a small percentage of a fire set I found on GitHub made by the user Care. The dataset consisted of JPEG files, which need to be converted into a readable format using the Python library CV2. I also resized the images to match the size of the images taken by our system's camera, which is 500 by 500 pixels. The dataset was then sent to the model to be utilized for training. The model was created and trained via a combination of the libraries TensorFlow and Keras. I found training a model to be extremely interesting due to the variety of variables to play with, which would in turn impact its overall accuracy. When first training the model, I did an experiment where I tested multiple densities, conversion layers, and node layers. The results produced models with accuracies from 48 to 96%. From this data, I was able to determine that the best trained model consisted of a single conversion layer with 32 nodes and a density of 0. I then did further experimentation to see how many times the network could run without overteaching it. This new training set produced the best results at 10 epochs, and I exported it as our final convolutional neural network. The CNN works by interfacing with node red and receiving an image every 30 seconds. It then detects whether there's a fire within said image. If there is a fire, the user will be notified immediately. This functionality provides the user with the freedom to place their system further away from potential fire risks, as the neural network will be able to detect the presence of a fire well before the temperature and smoke sensors.
So this first flow that we have is a main workflow that reads every 30 seconds. Effectively what this is doing is it's running a Python script that is grabbing from the Enviro hat the temperature sensors and the analog readings of the smoke inputs. It is then going through to get the latitude and longitude of the device, which is what this little section is here, and query for any nearby alarms. So this works, I'll open this up. This works by effectively grabbing any of the times where the alarm is on, and it is close to the latitude and longitude within the distance within the global radius. So that global radius is set here. So as you can see, as you drag that out, it kind of resizes itself automatically. So once that's done, it will store that in its little section, and it'll move that on. So then it has immediate checks. So these immediate checks are basically how we know if there's an immediate warning that we need to alert the system with. So quite simply, it's just checking if the temperature is over 40 degrees, smoke is over 4.5, because it's roughly from a 2 to 5 scale. And when we tested it with a LiDAR, we found like when there's gas in the system, it usually puffs up to about 5. And there's also our image detection, which runs. And again, if there are any nearby alarms. So any 4 of these triggering means that there's 1 warning. More than 2 triggering, or 2 or more triggering, basically means, okay, there's probably something really wrong, we need to actually deal with it. So we use a switch statement here to basically say if there's 1, then we set up a warning. If there's more, then we do the alarms, which is where it filters into all of this stuff. So we have an audio out that comes through, and we also have a status bar in our thing. So the audio actually plays through this window. We can set it to play off the device itself, but just for the purposes of this demo, we wanted to have it played in a way that you can hear. So we will go back. I'm going to cut this bit out, and time cut. Once those are all done, what we have is some insert queries. So we literally write up to insert the values of the temperature, image detection, and smoke into our database for like some sort of post-analytics. And then we also have an immediate thing which basically gets sent into the non-persistent graphs of the temperature of the past hour and the smoke of the past hour, which are displayed here. So you can see over time they update. They have like these little things that one just happened just then. And basically over the hour this graph grows and then starts culling off the last things. Yeah, the other two graphs we have based on that processing are also an analysis of the last week and of the last day. So you can see here, last week isn't too fancy because we've only been running it for about 2 days, so we only really have 2 data points. And the last day fluctuates a little. Because we've been running it in some varied environments rather than leaving it static, it probably varies more than it should. However, given that it's supposedly going to be in a static environment that shouldn't change unless there is an emergency, these can be used. Now we also have our map flow. So you can tell our big fancy map here, basically we have 3 things that are going into it. We have the radius of where our device is scanning, we have the thing that centers the map, and then we also have something that sets any warning icons. So I'll demonstrate those now. If we have a look at our debug flow, these are all the ways we can simulate things happening. So the first thing we're going to simulate is something happening on a faraway device. So because it's on a faraway device, there we go, I'll just refresh that. Because it's on a faraway device, you can see the little icon show up right here. That doesn't trigger a warning because we're not scanning for that distance. However, if we trigger something that is nearby, what should happen is when we refresh the map,
more sensors have indicated a fire.
I hope the audio actually picked that up.
Sensors have indicated a fire.
So that'll sort of keep running until we reset those alarms, just so it doesn't keep happening. And you can see that there's a little warning status that changes. So it changes from green to orange when there's a warning. And if the user so persists, they can sort of ignore it and hit a false alarm, then it resets back to static. One thing we can do, which is fun, is if you increase the range, now you can see that it will probably hit that faraway section. So refresh the map, and on the 30 seconds when it does its check,
Warning. One
it will
or
play
more
it again.
sensors have indicated a fire.
Warning.
One or more sensors have
Yes.
indicated a fire.
Thank you, it's very loud. I'm going to reset all those alarms again. So, the other last thing that happens is if multiple triggers happen. Because of just the environments, we can't actually start a real fire. So I've created this little demo alarm that basically will simulate what it would be like if this immediate check flowchart will affect it. When you hit this,
Multiple sensors have
so you can see there's a little alert there.
There is a high chance of fire.
There's an alarm, and then the other thing happens when you reset the map is this itself actually gets marked. So this all goes into a remote database. So effectively, if we had multiple pies set up, your pie can communicate with all the others, and it would tell when you're in a danger, and also when people around you are in danger. I believe that's everything. I'll talk about one last little bit. I'll talk about how we get the location. So how we get the location is actually from an exec command. So we use a little thing called where am I that returns a JSON. And then a JSON, so it basically stores everything's latitude and longitude. So if I create a select, you can actually see all of our registered devices have their ID, their latitude, their longitude, and whether or not there is a current alarm set off on them. That changes dynamically based on this alarm system we have discussed. So it will turn on, and then if you decide to hit the false alarm button or enough time has passed, it will reset themselves.
In summary, we believe this proof of concept is representative of a successful product and utilizes sensors, data recognition, and analytics to ensure the safety of the users while remaining understandable and usable. This was an engaging product for the 3 of us, and each of us filled unique roles in the ideation, design, and execution of the prototype. We learned that there is a lot of resources out there that can streamline the development of IoT software, and luckily we didn't have to reinvent the wheel. Finally, we learned the benefits of IoT devices in our lives, as they give the software we make a connection to the outside world.